All right, so to start lecture day, I want to talk about the assignment that's due on Thursday. So I'm expecting a rough draft of a 1,000 word write-up that you're going to do on the article that you selected. I posted the selections from everybody on Blackboard, so you can kind of get a feel of what everybody's going to be doing. I am not expecting it to be perfect. I am expecting it to appear as though you've put in a good deal of effort in terms of doing the background. I wrote on there kind of the things that I'm expecting in the report. Part of the purpose of this assignment, other than for you to write on there and to get interaction with industry professionals and to get some sort of knowledge of material that's going to be outside of the main course lecture, is professional development. I expect you guys to put a solid effort, try to write technically about this topic, and you're going to make mistakes. I don't expect it to be perfect. As I was going on my little spiel right before class, I have 25 publications, and I've done reviews for 51 journal articles, or 51 submitted journal articles. Not all of them were accepted, and the reason why is some people didn't take the opportunity to learn how to write or do good science, but that's neither here nor there. The important thing is you're going to get my article back, and it's going to have a ton of markup, so I'm going to have a ton of comments for you guys. That's okay. Don't be afraid to fail on this. The key thing is I want you to learn from it, so that way when you submit your final draft before you go out and post it online, is that you've actually improved your technical writing. If you're a good technical writer, that makes you more valuable than just being able to do coding or being able to write things on Blackboard. Not on Blackboard, because the key thing to take out of here is you can do all the good science you want, you can do all the good engineering you want, but if you can't tell people what it is that you did, then it's not really very valuable, right? You have to be able to convey what it is in your head. So that's the purpose of this assignment. So we ended lecture last class. We were talking about pi delay models for wires. So we did up through example question 4.9. And we started talking about this concept of wire energy. Now recall that the energy equation is the capacitance times the supply voltage. So when we consider the wire capacitance from example 4.9, we have 0.2 femtofarads per micrometer times 1.0 volts. So now what you have to do is you figure out the length of the wire, and then you can calculate its total energy because you've calculated its total capacitance. So we're going to go through this example, starting here with example 4.10. We have a 20 millimeter by 20 millimeter die, the microprocessor. It's running the engineers want it to run at 3 gigahertz in a 65 nanometer process. A layer of metal is rounded on a 250 nanometer pitch. Half of the available wire tracks are used. So that means at any given moment, we want half of the tracks being used. And as you recall from last class, we have this issue where we have wires either switching in the same direction, switching in the opposite direction, or not switching at all. And based on their switching, that contributes to capacitance, it contributes to power consumption. And we're going to be going over that a little bit more detail when we start talking about crosstalk. So to go back to 4.10, the wires have an average activity factor of 0.1. Suppose that the wire capacitance is 0.2 femtofarads per micrometer. Determine the power consumed by the layer of metal. So the way we're going to do this is that first thing we're going to do is we're going to find out the number of metal tracks. So we have the width of the die, and we have the pitch here, 250 nanometers. So this is 20 times 10 to the negative 3 over 250 times 10 to the negative 9, and that's going to come out to 80,000 tracks on this die. So we also know that half of them are going to be used. So 80,000 divided by 2 becomes 40,000. Now, We also assume that the length of the wire is going to be 20 millimeters because we have a 20 millimeter by 20 millimeter die. So the wires are going to go this long, like so. So here we have calculated our capacitance. We have 0.2 femtofarads per micrometer times 20 millimeters times 40,000 available tracks that are being used in a given moment. If you calculate that out, this comes out to 160 nanofarads. So now that we know our capacitance, and we know our switching factor, and we know our frequency, and we know our supply voltage, we now can figure out the power consumed. So we have our power of the wires is the switching frequency times the capacitance times the supply voltage squared times the frequency. So this becomes 0.1 times 160 nanofarads times 1 volt squared times 3 gigahertz equals 48 watts. So I've made a little note here at the bottom talking about power consumption. 48 watts is a lot of power. It's a lot of power for a die that small. And so the issue is going to be we want to regulate the switching factor in the circuit to bring this down. So if it's 0.1, that means every 10 clock cycles, half of the wires switch. Now, if you recall from pipelining, we're trying to mitigate the amount of wires that are being used in a given moment. And we do that through the use of control signals. So control signals ultimately try to reduce power consumption by mitigating the power consumed in any given moment. You can use clock gating, power gating. You can also, we learned a little bit about the wires being driven by the control signal. So if you have a load of 32 being driven by an inverter, like we learned last section, you can use that to mitigate power consumption. But so this example is an example of a poorly designed circuit. Yes, Adam.
The length of the wire, is it assumed to be 20 millimeters?
20 millimeters. Yeah, that is, of course, Thomas's comment comes back to haunt me. It is 20 millimeters, not 20 nanometers. Because it's 20 millimeters by 20 millimeter die. It's given in the problem. So I'm going to scroll up a little here because I want to talk about this concept of crosstalk. So in this problem we had 80,000 wires going across a 20 millimeter die, and here's the thing: when you have half of them being used and they switch next to each other, you now have holes and electrons flowing in opposite directions. So because of this, that tends to screw with the values in the wires. Now, if you dissipate too much heat and and the electrons in the wire are excited, you could potentially change the binary digital value of the full wire. That's bad, obviously. So this is a concept called crosstalk. So we've kind of described a little here. A wire has high capacitance to its neighbor, 0 to 1 or 1 to 0. Capacitive coupling or crosstalk. Noise on non-switching wires. So we have a wire that we want to hold at 1. We have another wire that was initially 0 going this way, and then we switch it to, I'll make it a better example. So that's 1 going this way, and then it's 0 going this way. Well, what happens if this is a poorly designed wire that has a lot of capacitance? It makes it significantly more difficult to switch this other wire to 0. And if it's not able to do that, then it'll stay at 1, and the result will be that the circuit has failed. So I'm going to show you a diagram here in a second of a circuit to describe what this circuit ground, circuit top plus circuit bottom is. So you have layers above and below. If you remember from last lecture where we had metal layers in the Intel 90 nanometer and 49 nanometer process, so we know that wires don't just run this way. They also run on top of each other. And we use different metals to try to communicate north and south versus east and west, horizontal and vertical. So we have to worry about the capacitances because we have wires going in different directions, and they have a certain amount of thickness between them. So now we've created a capacitance. So now we have to talk about the adjusted capacitance based on the behavior of its neighbors. So we have to worry not just about the capacitance of the wire, but the wires around it. And so we're going to talk about that a little bit of detail. So this concept of the Miller coupling factor is what I've been alluding to. So you have some sort of wire, and then you have the capacitance with respect to ground, and then you have the capacitance between the two wires here. So you have two wires, A and B. And now this concept of Miller coupling factor describes the capacitance of two adjacent wires and multiplied to find the effective capacitance. So what this means is that if the wires are constant, then the capacitance just is going to be the capacitance of the ground plus the adjacent capacitance. And so that's called a Miller coupling factor of 1. Now, if we switch with A, so that means A and B are both going this way, and then they both switch, the Miller coupling factor is going to be 0 because we're still just worrying about ground. However, if B switches opposite of A, meaning it's going like this and then starts going in the opposite direction, then the impact is going to be twice of the supply voltage because now it's going in the opposite direction. So the supply is the flow of the electrons through the materials going this way, and now you've switched it going the opposite direction. So now it's the opposite voltage, opposite supply, therefore it's 2 PeV. So the effective capacitance becomes ground plus 2 times the adjacent capacitance. And therefore, this is defined as having a Miller coupling factor of 2. I'm going to scroll up to here. So when, on average, you want to have a Miller coupling factor of 1.5. So when you're trying to estimate your designs, and we'll show you an example of this in example 4.11 here, of what happens when you want to have a lower Miller coupling factor. So either when they're switching, do you either want them to kind of switch in the same direction or opposite? But mostly they're going to remain constant. So where that comes from is mostly they're staying constant because if you think about it, you want the buses flowing in the same direction through the data path. However, sometimes the wire is going to be off, so therefore you go down your Miller coupling factor of 0. Or you have an instance where they go in the opposite direction, and the opposite becomes 2. So on average, it becomes 1.5. Does anybody have any questions on this before we go to the next example?
Does it only affect adjacent?
It depends on the, this is a good question. So it only affects adjacent wires because here, let me draw this out so I can answer your question. So if you have a wire, right, and then you have an adjacent wire. So now your capacitance is between these two and you have another one that's here, right? And then if you want to do this in 3 dimensions, you have another wire and the capacitance is from this wire to this wire down. If you have another wire, the capacitance is going to be between these two. So the capacitance would affect these wires, but the only way, if you had some sort of insane amount of capacitance here, that if in order for that to happen, now that I think about it, you would have to you pretty much have to violate the lambda laws that we talked about in section 1, because you'd have a huge wire consuming a lot of power in order to be able to impact a wire that's not adjacent to it. So, does that answer your question? Okay, good. Okay, so let's discuss this example, and this is going to conclude section 4. Each example 4.11, each wire in a pair of 1 millimeter lines has a capacitance of 0.08 femtofarads per micrometer to ground and 0.12 femtofarads to its neighbor. So now we have our adjacent capacitance is 0.12 femtofarads, and the capacitance to ground is 0.08. Each line is driven by an inverter with a 1 kilo ohm effective resistance. Estimate the contamination and propagation delays of the path. Neglect parasitic capacitance of the inverter and resistance of the wires. So we have some sort of wire here that we are driving an inverter here at the end, right? So first things first, we want to calculate our ground capacitance on our adjacent capacitance. So we do this because our units we're given capacitance per micrometer. So 0.08 femtofarads per micrometer times 1 millimeter becomes 80 femtofarads. And then the adjacent wire that's running along is 0.12 femtofarads per micrometer times 1 millimeter becomes 120 femtofarads. So the contamination delay is the minimum possible delay which occurs when they switch in the same direction. So now they're going in the same direction here. So the contamination delay is going to be equal to the effective resistance times ground capacitance. And if we recall this from the previous topic we got objective, the Miller coupling factor is 0 when they're in the same direction, right? So in their opposite direction, we're going to be 1 plus 2 times the adjacent capacitance because we're going to have a Miller coupling factor of 2. And if you do, I know some people complain when I scroll around like this, so I'm about to scroll, people watching on the video. This is where the equation comes from, here. And so you multiply that out, that becomes 80 picoseconds. So here, this is when your Miller MCF is equal to 2. And that's because it's ground plus 2 times the capacitance of the ADJ, right? So this becomes effective resistance times ground times 2 adjacent, which is 1 kilo ohm times 80 femtofarads plus 2 times 120 femtofarads, which we calculated here. And that becomes 320 picoseconds. And so here we define the propagation delay as the maximum possible delay, which occurs when they switch in the opposite directions. So contamination delay is when it's not contributing to the logical calculations of the circuit. So that's the minimum delay. So you have one wire going, the other wire is off. The propagation delay happens in this wire when it's going this way and it is fighting the capacitance of the next adjacent wire going in the opposite direction. So when you have the wire going in the opposite direction, we end up adding 240 picoseconds of delay. Does anybody have any questions on that?
What was the constant situation again? What was with the wires when we have a MCF of 1?
When you have an MCF of 1, when they're constant. So basically, you have, there we go. So we have 2 wires, right? So if both of them are on, right, and they are going in the same direction, that is 1. When you have 2 wires and one of them switches and the other one is just off, then the coupling factor is 0. It means they're not coupled because it's off. And then when you have 2 wires, and one switches this way and one switches the opposite direction, that's this.
Switches the opposite direction?
Yeah, they're switching they switch simultaneously in the opposite direction. Or once they're going in the same direction and then A switches. So both of those apply. Yeah. Okay. Does anybody have any other questions on this? All right, so in this section, we're going to be talking about combinational and sequential circuit designs. So now, to this point, we've kind of gone into PMOS and NMOS transistors. In where we're going to find here is static CMOS. So if you've kind of noticed, PMOS transistors, here we go. PMOS transistors, come on. Technology, we're making it better. Okay, so if you recall from just your conventional inverter, right? And that the width length ratio is 2 to 1. And when you have a 2-input NOR gate, right, it becomes 4 and 4. And then the PMOS goes to 1 and 1, correct? So in the olden days, before we came along, before we were all born, like 1960s, somewhat, that kind of time frame, they actually didn't really use PMOS very much in these kind of circuits because PMOS has a lot of, it drives a lot of capacitance. And if you're worrying a lot about power consumption, especially if you're working for NASA, and you're trying to design a computer chip that will go to the moon, and you can't just, Buzz Aldrin and Neil Armstrong need to replace a computer chip, well, let's just send IT. No, not going to happen. It needs to consume low power, and you're not going to be able to replace the battery. So we also know that because of this, NMOS transistors provide more current than PMOS. So we want to try to take advantage of this idea here that logical effort tells us that NAND gates are better than NOR gates, and that gates with fewer inputs are better than gates with many inputs. So we're going to be talking about certain ways that this has been addressed through what are known as circuit families. Specifically, we're going to be talking about something called pseudo-NMOS. We're going to be talking about domino logic. And everything we've learned up to this point is what's known as static CMOS. So how is the PMOS transistor reduced in size and then biased in order to try to reduce power consumption in the circuit? Now there's trade-offs, and we're going to be going into that. Specifically, these circuits run a lot slower than your typical CMOS circuits. And we've kind of talked about this already, that electrons have twice the mobility of holes, so therefore we have to size the PMOS twice as much. All right, so we have defined static CMOS as the conventional CMOS family where there exists at all times some mechanism to drive the output either high or low. And this is going to become important when we start talking about dynamic logic, because dynamic logic has something called moneticity. And what moneticity means is that the output has to be greater than or equal to the input. And so for example, in digital CMOS, if the input's 0, it can be 0 or 1, that's fine. But if the input is 1, it can be 1, but it can't be 0. And when we go into the physical layout of the design, this will make sense. But it has a lot to do with what's known as pre-charging and enabling. So if you try to pre-charge a circuit, and you've already pre-charged it to a point of 1, and then you try to drive it down to 0, it's not going to work. So you have to use something called domino logic in order to be able to get around this. And so what we're going to cover for the rest of the combinational portion is dynamic CMOS, which explains temporary storage of information and stray and gate capacitances to drive the output. So we have these output capacitances. So if you're doing something adiabatic logic, which is kind of outside the scope of the course, the whole idea is that you're trying to recycle energy. So what you're going to do is you're going to have a positive and negative voltage. So we've learned about 1 and 0. So they're going to have VDD and then negative VDD. And then what's going to happen is you're going to have your 0 to 1, it's going to go to VDD. And then you drive it down to 0, what's going to happen is it's going to dissipate the capacitance towards negative VDD, which will then create a current which will represent a 0 logic. So it's trying to recycle this energy instead of just dissipating into the environment. So as we just learned in section 4 about wires, that if you're dissipating energy into the environment, you're increasing the Miller coupling factor and consuming more power and potentially changing the value. So something that's going to really help with these types of problems is this concept of bubble pushing. Bubble pushing just exploits the Morgan's law. So we've kind of already learned this. So these are back and forth. This is a NAND gate and with an OR gate with two negated inputs are identical. And we know that in the OR, so we have an OR gate, right? And we have to do this, we'd have to have two inverters. So we have two transistors, and we know that an OR gate is a NOR gate with 4 transistors plus 2, right? So now we have 2, 4, 6, 10 transistors, or what's logically equivalent to 4 transistors. And we also know that the NAND gate has two PMOS with 2 lambda, and then 2 NMOS with 2 lambda, whereas the NOR gate has 4 lambda, 4 lambda, 1 lambda, 1 lambda, and then you have to have 3 inverters. So by taking advantage of this bubble pushing, you're going to significantly cut down on the power consumption. And we're going to go over an example here in a moment to describe precisely how bubble pushing helps reduce your power consumption in your circuit. So example 5.1, these are all just to describe, these are all the steps to get to the final solution. Using only NAND, NOR, and NOT gates, since we know those are the smallest ones, design A, B, or C, D using bubble pushing. Next, calculate the path, effort, and parasitic delay. And we're going to be doing that down here. Each input can present a maximum of 20 lambda of transistor width. The output must drive a load equivalent of 100 lambda of transistor width. Next, design NOT A, B, or C, D using a Cmos pull-up, pull-down network. Using that design, calculate the path, effort, and parasitic delay of a Cmos inverter added to make it A, B, or C, D. Next, find the minimum delay of both circuits. Choose transistor sizes to achieve this delay. So what we're going to do here is we're going to be using this concept of bubble pushing at the gate level, and then we're going to go down to the transistor level and design the same circuit, and then we're going to see the pros and cons between sizing and parasitic delay. So the purpose of this problem is to show you these trade-offs in design that you need to be able to make. So here, A and B or C and D is simple. A and B, C or D, and then they're both ORed, right? So what happens is since we used to use NAND to make it logically equivalent, we just put a inverter, right? So it's NAND and then inverted to make it an AND, right? And so this becomes NOT and negated here. So then we do this bubble pushing. So now we have our bubbles here on the NOR gate. Well, guess what? We can just reduce that here a step further. And then finally, this becomes another NAND gate. So what's gone on here is we have NOR, then they're both negated here. Since we can get rid of, at this point, we can get rid of these negations. This becomes a two-input OR gate with negated inputs, which then becomes a NAND gate. So by using bubble pushing, we have reduced our initial number of transistors from 6, 6, and 6, right, to 4, 4, and 4. So we've cut out 3 transistors automatically. So our path electrical effort comes from our input versus our output. So if you recall, it's 100 over 20 lambda, which is what we have here, so that becomes 5. There is no branching because all paths lead to the same output, right? So the branching is just going to be 1. And then we use our NAND gates, NOR gates to calculate our circuits here, right? So we have 2 plus 2 over 3 plus 2 plus 2 over 3. So it becomes 16 over 9. And then our parasitic delay, we know that the 2-input NAND gates are 2 plus 2, so it becomes 4. So our path logical effort becomes G times H times B, which is 16 over 9, times 5, which is our path logical effort, times 1, which is our branching, which becomes 80 over 9. So to go back to where I asked the problem, I say next design negation of A, B, C, or D. So that's, I've done it this way so that way we remain constant with how we've done it previously in the course, where we do the negated values and then add the input to maintain the good design principles of pull-up and pull-down networks. So here what we have done is we know that it's not A or not B. So by using our design, we have our, right? And so we know it, ands are in parallel for PMOS and ORs are in series for the pull-up. So it's A or B, right? A, B, and then they tie here. And then they are in series with C and D, which is what we have here. Now for pull-down network, it's going to be to the output. So we know that ands are in series, so this becomes A and B, like we have here. And they are in parallel with what we are ORing, which just becomes C or D. Right? And while I'm bringing this up, we also know that we multiply the PMOS in series by 2. So we know that we have 2 in series, so it becomes, each width becomes 4. NMOS, we add them, so this will be 1 plus 1, so each one becomes 2. So that's how these transistor sizes came to be. So here we have 4, sorry, I circled the wrong 2. 4 plus 2 over 6, and then to make it the same ratio as an inverter, it becomes 6/3, which is how we got this number, times 3/3, which is the logical effort of the inverter. That becomes 6/3. So that becomes F, that becomes G, our logical effort. So go back. We still know the same circuit as before with our 100 lambda to 20 lambda driver. So this becomes 6/3 times 5 times 1, which becomes 10. From here, now this is where I'll kind of read this out loud to you guys. The parasitic delay is crudely estimated from the total diffusion capacitance on the output node by summing the sizes of the transistors attached to the output. So here we have 4, 8, 10, 12, and then we make it to the ratio of the inverter. So the parasitic delay becomes 12 divided by 3. And as a little note, and you can use this as I refer to it, this derived circuit is known as a AND or inverter 2 gate. So you have 2 inputs, 2 parallel here. So again, so here's the next step. I'm going to scroll back up just for a moment here. So here in the problem, we have designed the negative A and C. Here, so using that design, calculate the path effort and parasitic delay of a CMOS with CMOS inverter added to make it A, B, or C and D. So what I'm doing here to account for that part of the problem is add 1 to account for the inverter. So this becomes 12/3 plus 3/3, which becomes 15/3, which becomes 5. So now we're going to calculate our delays based on our NAND-based circuit, which is what we previously did, which is what we asked for. So it becomes number of stages, which is 2, times 80/9, which we calculated up here, times 1/2, because that's our number of stages, plus 4, because we calculated the parasitic delay to be 4, and that becomes 9.96. So these numbers come from 80/9, 4, and then 2 stages. For the AOI, we have 3, because we have 1, 2, and then an inverter here, right? So that becomes, I'm sorry, yeah, 2. Because we have 1 gate and then an inverter. My apologies. So this becomes 2 times square root of 10 plus 5, which becomes 11.31. So in order to figure out the final circuits, what we need to do is calculate the best stage effort and then the input capacitance. So the best stage effort just becomes F to the logical effort to the number 1 to the square root, or the 1 over number of stages power, 1 over n. So we calculated 80 over 9. So 1/2 becomes 2.98. Here we calculated 10. Where did I calculate 10?
It's up above the parasitic delay.
Oh, there it is, right here. 10. Becomes to the square root. So this number there, and 80 over 9, which is just the calculated just here at the top. That's where that comes from. So the reason why I calculate those numbers is to find the input capacitance. We do G times C out over F, which is what we just calculated here. So for the NAND-based circuit, which is our original circuit, it's 100 times 4/3, which is because we have an AND gate on the output, divided by 2.98, which we calculated here. So this is NAND gate, 2.98 is 44.74, and we're going to use 44 there, and I'll show you why in a second. For the AOI 2 gate, same thing. Output gate capacitance times, so G, C out over F. This becomes 100 times 1 over 3.16 for the AOI 22, and that comes out to 31.64. And here I say use 31. And the reason why, when we get to the final circuits, so this is where we come into play. We have for the NAND-based circuit, we have a shorter delay. So this is the delay of this circuit here. So this is when we take our lambdas here. So this here where I say use 44, if you recall 44, this is going to be, we have 2 lambda and 2 lambda, right, for each one of these. So this becomes 44 equals 4 lambda. Lambda equals 11. So we just multiply 11 times 2. We get 22 and 22. So that's how we get that circuit. Taking this value here, 31, recall for an output of an inverter, which we're using to drive, right? We have 2 lambda and 1 lambda for the inverter. So this becomes 31 equals 3 lambda. So lambda is going to become 10.3. So what ends up happening is they made the output 21 and 10 to make that work. So here's the trade-off. This circuit is much smaller, but the delay is higher. Right? So if we're in that Cmos class that I took at University of South Florida, and the design constraints are it needs to make it in the pad frame, and the winning group is the group with the smallest design, but it only needs to run at 1 kilohertz. Which one of these two are you going to pick? Yeah, you're going to pick this one on the right. So this is where I would go through and just use these designs, and it works fine. Because I don't care. It's 1 kilohertz at the 0.25 micron process is easy. But if your design constraint is frequency, and you have some sort of value that you need to meet in terms of delay, you're going to use this one because you have shorter delay. So the purpose of this problem, the way I've phrased it out, is I want you to start out with some sort of logic that you've learned in basic digital systems and advanced digital systems, and you're going to compare A and B or C and D. You design it out, you figure out the delay, you figure out the logical effort, branching effort, and from here, then you take what you've learned in this course at the Cmos level, design your circuit, figure out the the delay through the logical effort and the branching effort, the electrical effort. And what we figured out is based on this, we were able to figure out a delay, we were able to figure out the precise sizes of our output capacitances based on the values that we're given. Yes, Thomas. Laughing at whatever's on your phone. Yeah, okay. Just don't disrupt the rest of the class.
You can say a word. Call me fat.
Laugh like a pig. Not that I should talk, but does this make sense though? Like, does this make sense? Does anybody have any questions on it? I know I'm throwing a lot. This is a big combining concepts question. Yeah, Terrence.
Do you always round down on that? Or
Yes.
you just always, no matter what you
Yeah,
want?
because the reason why is because this is tying into the lambdas, and now if you're meeting 31, then you're meeting the constraint. So here you want to round down to try to reduce, because if you're rounding up, you're increasing your capacitance, you're increasing the amount of delay. Everything goes wrong from there. So you want to use these approximation values. Because ultimately you're trying to meet your lambda-based rules. So that's why we're going from some sort of decimal value down to a basic value. Because when you do polygon-based design, you're not going to be able to go 31.64. You're going to have to stick with these lambdas.
So even if it's at like 31.9, you would still go
Yes.
31.
Mm-hmm. Not until you actually get to 32.0. That's a good question. Okay, so does how I phrase the question make sense too? Okay. So up to this point, section 5 is where we kind of just keep digging, and we're going to finally kind of hit the bottom here of how low you can go in these designs. So up to this point, everything we've assumed is both inputs get there at the exact same time. But what we're going to find out is that if you design circuits where you don't account for this concept called asymmetricity on the inputs, you're going to get occasionally bad outputs. You're going to get values that toggle, especially when we get to sequential designs. This becomes really bad because you only want it to toggle when you have you've enabled the signal and then you've got your Q inputs changed. So we're going to define this concept of an asymmetric gate, and actually, to be honest, every single NAND gate that we've done so far is asymmetric. We're going to design a symmetric gate that works just exactly the same, but will work no matter which A or B input gets there. Asymmetric inputs inherently favor one input over another because one input sees less capacitance than another. So here we have, as example 5.2, we have a 2-input NAND gate. And the question states we're going to describe the following output transition that occurs when one input is held as stable 1 and the other rises from 0 to 1. Which input does the circuit favor? Your answer should describe both input A rising and B rising. Next, redesign the circuit to be symmetrical and prove it is symmetrical. So for the solution, for this particular circuit, we have input A is here and here, right? A input rises last. We also have this node X. So now in the problem, I refer to this node X here. Node X will initially be at 0 because B is 1, right? So when B is 1, we have it's going to be initially at 0 because we have these values here. Because it was discharged through the NMOS transistor on input B. No charge must be delivered to node X. So we have this instance where we're switching from 1, 0 to 1, 1 on a NAND gate. So the only times that we want, if we're at 1, 1, that's when we want a 0 to be on the output. So what we're trying to figure out is, because of the A gate here, A being here as opposed to here, it's dependent on B to be able to switch out. So what's happened is B already has a 1 on the input, and so this means it's an NMOS transistor. That means it's on. So we already have some value that's being held at X. And then when it's 1, we're going to go to the output. So what we're going to see here, and kind of give you a preview, when B rises last, B is actually going to take longer because we have to actually wait on A. So if B rises last, sorry, if A rises last, node X will initially be at 0 volts because it was discharged to the NMOS transistor on input B. Node charge must be delivered to node X, so the Elmore delay is simply R times 6C, which is our 6C output here, because we're combining both the PMOS transistor from A and B. Here, for B, we don't have, the A is already switched, but B is switching last. The node X will initially be at VDD minus VT because it was pulled up through the NMOS transistor on input A. The Elmore delay is going to be R over 2 plus 2C plus R6C, which is going to be 7RC, which in this case is going to be approximately 2.3. So these are the important numbers here, 6RC, 7RC. What this means is because of the B input being closer to the ground, it has to worry about another capacitance. It's because we recall from our Elmore delay, we have our input, we have a resistance, we have a capacitance, and then we have a second input and a second capacitance. And that these add up, the second one is R1 plus R2 times C2. So that adds up, so that's where why it doesn't, it's going to favor A as opposed to B because it has to go through 2 resistances here. And so the circuit's going to favor input A. So here's what we're going to do. We're actually going to split up the NMOS transistors into parallel 1 lambda NMOS transistors. And the way this is going to work is we're going to have one of these transistors from A tied to the output, and one from B tied to the output, and one from A tied to ground, and one from B tied to ground. This still adds up to 2, this still adds up to 2, and the inputs are still driven by the same amount of, it still drive the same amount of unit capacitance. However, what's going to happen is, because the Elmore delays are going to be calculated so that both A and B are going to have that 7RC, you're going to have a symmetric gate, which means no matter which one switches first, and see if I can, I'm going to zoom in here. So this is our symmetric gate. And you can see that A hits this one, and it's also going to go to the input of here, so it's tied to ground and the output, right? B, here this one's tied to ground, and this one's tied to the output. And then both A and B on PMOS are tied to the output. So this is still 6RC here, and then 7RC, right? So they're going to rise equally.
Did we have a TGO 5.4 or did it just get skipped?
Great. Yeah, it did. Yeah. I'll just write magic for 5.4.
We'll do that too.
Do it. Or you don't have to. I'm not going to take off points. But. Yes, Jason.
And the Elmore delay, you're getting 2. What are you using for R?
So the resistance of the capacitance. If we go back to section 4 here, I can show you at the very beginning. Where's cancel? Done. So you can find it. Oh, and it's not section 4. It's going to be section 2, actually, because remember RC delay? Yeah.
I can do that.
Yeah, that's...
Yeah, sure.
Because if we recall from, it's example 2.1 where we calculated the RC delay of an inverter, and it's 6RC. Refer to that problem. So we've defined this concept of skewed gates here. They inherently favoring one over the other. Now, high skew tends to favor the rising output transition, and low skew tends to follow the low output transition. So this isn't just which input gets there faster. It's, are we favoring when it goes from 0 to 1, or are we favoring when it goes from 1 to 0? So we have three sets. We have an inverter, a 2-input NAND gate, and a 2-input NOR gate. So these first ones here are not skewed at all, meaning that they will favor both high to low and low to high equally, and we've calculated those out already. High skew, meaning it's going to favor from rising, so it's going to favor from 0 to 1. And as you can see, the NMOS transistor lambda has gone down in this design. So it's still going to pull up the to 1 just fine because it's going through the PMOS transistor, but 1 is going to require a lot more effort. So it's going to favor the rising transition as opposed to the lower transition. With a lower lambda on the NMOS, what's going to end up happening is it requires a lot more effort to keep it down at 0. So it's a high skew circuit. And then what you're going to see in this low skew circuit, we've reduced the size of the lambda on for the inverter. And for the PMOS and NMOS for these circuits, you'll actually see that for the high skew, the PMOS has been reduced. I'm sorry, for the high skew circuits, the NMOS has been reduced because it's harder to keep it at 0. And for the low skew, the PMOS have been reduced because it's harder to keep it at 1. So these are just examples of how it works. Now, we're going to start going on, like, how can we actually reduce these PMOS transistors? Now, the key detail, if you notice that the logical effort in the NOR gate here, so when we reduce the size of the PMOS, notice the comparison of the logical effort here compared to here. That means we're reducing capacitance. So we're able to reduce power consumption. Now, if you recall, current is also has a relationship with the capacitance. So what we're going to be finding out in these circuit families, specifically when we start talking about pseudo NMOS and domino logic and dynamic gate, is we're going to have a trade-off between lower power consumption and current delivered, which means ultimately we're going to have a trade-off between power consumption and delay. So if you have a lower delay requirement, you're going to use some of these circuit families. If you're trying to get into, if your performance is your most important design metric, you're going to be wanting to stick with static CMOS. So here I've talked about these PN ratios. These are the optimized PN ratios here for PMOS to reduce input capacitance and average delay. So here for an inverter, it's been reduced actually to the square root of 2. And our effort up, and because we're dealing with skew, so they don't do this, they don't have the same logical effort. The effort going up is 1.14, and the effort for pull down is 0.80. And the average is are those average, so it becomes 0.97. And that's a relationship to a conventional unit inverter. So 3/3 becomes 1. Likewise, for NAND gate, where we've pulled down, we have 4/3. Actually, the conventional NAND gate is the already optimized gate. And then here, we reduce the PMOS from 4 to 2 in NOR gates. So these families, particularly when we talk about pseudo NMOS, they're going to, where they really help out is reducing the size of NOR gates, because we already know that NAND gates are optimized. So to read these a little further, the effort for up on NAND 2 gate is 4/3, down is 4/3, and average is 4/3. which we've already proven in class. And here, the pull up is going to be 1, it's going to be 2, as opposed to 4. Pull down is going to be 1, and then the average is going to be 3 over 2. So this last little detail here that I'm mentioning, like the delay improvement isn't going to be very high. However, because we're getting significant reduction in Pmos sizing, you're getting significantly reduced area. So if you were designing a circuit where area is not as important of a power consumption, but power is, where performance is not as high of a power consumption, I'll say this again. If performance is not as important of a metric, meaning that you're running something at 13.56 megahertz, for example, like smart cards. However, you're trying to reduce the area of it as much as possible because it has to fit in a small chip that people can carry around with them, and has to consume low power. Some of these circuit families we're going to talk about are optimal.
So you would say like big three constraints for designing something would be the frequency, the power consumption, and then just the size of it.
Yes. We'll also in section 6, we're also going to be learning about design corners. So we're going to be learning about how process variations also affect that. So if we recall from section 1, we looked into lithography, how you actually dope this inconsistent doping, inconsistent portions of the circuit, how that affects the temperature throughout the circuit, how the voltage distribution is affected throughout the circuit, and those are all reduced by reducing the amount of area. So, and then ultimately temperature of the area. So yes, those are the short version. The short version of your question is yes. So you see, we've kind of come up with these different ratios. So we're going to be talking about this concept of ratioed logic. Ratioed logic is any CMOS family where the VOL, so that's our lower noise margin for output, is determined by the beta ratio, beta P over beta N. And we're going to discuss 3 here. The first one's going to be called resistive loading. The second one is going to be our pseudo NMOS. So let me scroll up here. So for 5.8, this is called a resistive load. So we put some sort of just constant resistive load here. Our VOH is just going to be VDD, but we're trying to get VOL here. So we have the resistance of the pull-down network. So here, our pull-down network is going to be NMOS transistors, because ultimately we're trying to reduce the PMOS, because PMOS is our biggest contributor to area and power consumption. So our pull-down network plus our load times the supply voltage becomes the value that we want for VOL. So we're trying to get down, ideally, to approximately 0.2. So we have some sort of voltage, let's say it's 1, and then VOL is where our noise margin is sufficient that we're able to properly represent a logic 0. So we would try to calculate 0.2. We know the NMOS circuits that we're going to want to design. So if we have a 2-input NOR gate, we have 2 NMOS transistors in parallel, and then we're going to calculate their effective resistance. And then by doing that, and we know our supply voltage, we can calculate the resistive load that we would need in order to be able to make our noise margin. And then these numbers should all look familiar for rise and fall times, because we've calculated out in section 2 this value 0.69 RLC, and that contributes to delay. So the amount of time it takes, typically 0.69 times the effective resistance times the capacitance. And this description here, RL parallel PDN, is just this calculation. Does anybody have any questions about this? This next one is called depletion load. So here, what we're actually doing is we're tying the value that we want on the output to the gate of the PMOS transistor. So we're going to have some sort of PMOS transistor acting as a load. And what we're going to find out through calculation is that we're able to significantly reduce the width of the PMOS transistor. We just have one, just like here, the pseudo NMOS, which we're going to describe next. Only one PMOS transistor. And we're going to use depletion mode for pull-up. So the idea is that the depletion mode transistor is always on, and the source gate VGS is going to be 0. And so when you pull it up, we want 1 on the output, right? We're going to use the pull-down network to achieve this. Because it's going to be tied to ground. Now the important one that we're going to be covering and we're going to be doing for the rest of the section here is this pseudo NMOS in 5.10. What the concept of pseudo NMOS is, we're going to get rid of this hook here, and we're just going to tie the PMOS to ground, meaning it's always going to be on. So our switching and our getting the value of 0 on the output or value of 1 on the output is going to be dependent on how we design the pull-down network for NMOS transistors. So if we were to do a 6-input NOR gate using this pseudo NMOS, we just have a 1 PMOS transistor, and it's going to be tied to ground. Then we have our output, and then we're going to have 1, 2, 3, 4, 5, 6, and then they're all going to be tied to ground here. So we have to size it because when we're going to do this calculation here, it's always going to be on. So in order to obtain a 0 on the output, we actually have to have an instance. When it's 0 here, this means that PMOS transistor is going to be in saturation mode. So we're going to have a saturation mode PMOS circuit and then linear NMOS circuit. So since we know the currents are going to be identical, we're going to set them equal to each other, and we're going to calculate the ratio. And then through experiment, we're going to prove that that's going to be 2/3 for PMOS and then 4/3 for the NMOS. So we're going to reduce the size from 2 to 1 to 2/3 and 4/3. So the pseudo NMOS, the PMOS is always on. It's going to make PMOS about 1/4 of the effective strength of the pull-down network, and we're going to prove this. VSS is ground, and then this is an example of 3 inputs for a pull-down network for NMOS transistors. Okay, I'm going to scroll up. Well, actually, can I do that? Yeah, I can do that. I'll just hold it right here. So here's the important thing. So if you see at the bottom where we have all these calculations, what's going on here is we have these different plots with a relationship of output voltage, the input voltage, and the width-length ratios. One of the things we're going to find from 1/4 is that this is the plot all the way to the left, is that it's able to hit the noise margin quicker here, right? So, yeah, I can scroll up here. So if the length-width ratio is 4, then we have a very quick delay. But if it's 1/4, we're going to have a very slow delay. So this is where we make our comparison. However, you see we're trading off delay. The delay is going up when we go like this. However, power consumption is going down. So the trade-off in this design is we're going to be trading off delay with power consumption. So it's going to be running slower, but it's going to consume less power. So this is going to be example 5.3. This is going to be the proof that we're going to be working on. We have consider a NMOS, pseudo NMOS inverter is 0.18 micron technology with a 1 volt power supply and 0.27 volt threshold voltage. We're going to find the beta ratio for this device considering we want a VOL noise margin of 0.1 and considering that the output should be reduced to 1/3 for the pull-up network. I should state here, the best size process, but it's usually in the range of 1/3 to 1/6. Through experiment, they've determined that the best ratio is approximately 1/3. So what we're going to do is we're going to do the beta ratio, and then we're going to divide those by 1/3 to get our final design. So we know for PMOS, with our gate source and drain, that when D is 0, meaning when D is 0, that means our output is going to be 0. So we have, it's tied to volt, VDD, the output is 0, but the PMOS transistor is still on. So what we know is a V source gate, so V VDD minus 0 is going to be VDD, and source drain is going to be VDD minus 0 is also going to be VDD. Therefore, if we recall our definitions on linear saturation and cutoff, when VDS is going to be greater than, VSD is going to be greater than VSG minus the threshold voltage. So it's going to be VDD, it's going to be greater than VDD minus VT. We have met saturation. So in the instance for NMOS transistors, we're either going to be in linear mode when we want the 1 on the output, but we want PMOS to be in saturation when it's going to be a 0 on the output. So therefore, we want NMOS to be linear and PMOS to be in saturation. So we're going to be going back, good combining concepts type question. We set these currents equal to each other. The beta ratio of VGSN minus VTN minus VDSN over 2 times VDSN is equal to, for saturation, beta P over 2 times the quantity VGS P minus VTP squared. So when we solve for the beta ratio, what we're going to get is this equation, where it's going to be 1/2 of gate source P minus VTP squared over VGSN minus threshold voltage of N is VDSN over 2 times VDSN. Now, we know that for this circuit, VDSN is going to be the comparison between the ground and the output, right? So when we want to get to VOL, that's going to be the difference between ground and the output. So we're going to substitute VDSN with VOL. VGS, right? We want to have a 1 on the gate for NMOS transistor. So that means it's going to be on. So VGS is going to be equal to VD. And VGSP is also going to be equal to VDD. And the reason we know that is we want this one to be VDD and ground, and the PMOS is tied to ground. So V source gate is also going to be VDD. So we can use our knowledge of that to actually substitute these values substitute these values into this equation. And then we get 1/2 of VDD minus the threshold voltage of the PMOS transistor squared divided by, and for here I took VOL and then multiplied it through. So this becomes VDD minus VTN output low minus 1/2 VOL squared. So we are given these numbers from the problem. We are given a supply voltage of 1 volt, threshold voltage is 0.27 volts, and a VOL output low range of 0.1. So when we plug that into our equation, it's exactly, it's 3.918, but it's going to be approximately equal to 4. So therefore, we're going to have the beta ratio. But recall from section 1, we still multiply the PMOS by 2. So what we're going to end up having here is we're going to have PMOS 2 NMOS of 4. But I kind of mentioned here, and I mentioned earlier, through experiment, we were able to determine that the current is 1/3. And if we recall, we know that TPD is approximately equal to the capacitance times dV over dt, right? So that's going to mean that the current is also going to come down by 1/3. So here, I is going to be equal to C dV dt for reducing the current by 1/3. That means we reduce the capacitance by 1/3. So therefore, our final circuit, where we have A as the input, we have our PMOS transistor tied to ground, and we have a 4/3 and a 2/3 on our output. We're going to go over 5.11, and then we're going to conclude. Just so you know. Okay, does what has what I've done make sense, or at least I see a lot of people kind of nodding off today. It's that week right before spring break. It's understandable.
Today was a lot. Like way too much today.
Just life for.
Particularly this class.
Well, that's what happens when you put off, when you give you 5 days to do an assignment, you wait till the night before to do it.
Now you're
Not-
assuming.
I am not assuming.
I'm talking about the lecture.
Well, lecture, yeah. This is heavy material, but this is kind of as deep as it gets. When we at section 6, we're going to start talking about autons. Thomas, come on, man, we've got 5 minutes. So does anybody have any questions about this?
Not yet.
Not yet. I'll go back through. All right, so the last thing I want to cover is 5.11. So here we have actually proven this, right? We just proved this from, and these are our pseudo NMOS inverter, 2-input NAND gate, and 2-input NOR gate. So the difference is we're only using one PMOS transistor. And for all of them, it's going to be 2/3. So say 2/3 every single one. And we're going to keep the same rules as before. We're going to add up the NMOS transistor. So when we're doing our NAND gate, the NMOS are in series, right? So it just becomes 4/3 plus 4/3, right? So it becomes 8/3 for both of them. Same thing, these are 4/3 and they're in series, because ultimately they relate back to the unit inverter. Now, these efforts, because of the fact that we know that they're skewed, and we know that they're asymmetrical because they deal with one input on the NMOS only, they're going to have differences between their effort when you pull it up and the effort when you pull it down. So for the inverter, it's 4/3 up, 4/9 down, and the average of those, which is 8/9. Your parasitic delay for up is 6/3. Your parasitic delay for down is 6/9. And the average is just the average of those. For the NAND gate, the up is going to be 8/3, down is going to be 8/9. The average is 16/9. The parasitic delay is 10/3 for up, 10/9 for down, and then average is 20/9.
What does the G stand for?
Effort.
Effort, oh.
Yeah, same thing as before.
Okay.
And then, last but certainly not least, up for the NOR gate is going to be 4/3, down is going to be 4/9, Average is going to be 8/9, just like you see here. However, the delay matches these. So does anybody have any questions about this? So TGOs are not due until after spring break. This stuff in class is not due until you get back, so you have a week plus to get familiar with it when you're out on the beach. And what I do want is a rough draft of your 1,000-word blog post.
And Dr. Morris,
Yes.
you want us, what format? Do you want us to bring in a
I
physical copy?
I do want you to bring in a physical copy because I want to make markups.
Okay, yeah. And
And you want every member of the group to write one? Or
No. I want you guys to get together and write them. Yeah. Yeah.
Do you want us to email it to you as well? Or?
No. Make them bring them to class. Okay.
What was the
And yeah, and I'll post this, but it is the TGOs. Don't worry about those until after spring break. It's designed this way because I know that Section 5 is heavy material, so I know that this will give you more time to kind of work through it.
Yeah.
Hold on, let me close out.